Good morning. We are continuing with synchronous motor drives. In the last lecture, we had taken a look at the power angle relationship of a synchronous motor drive. We had also taken a look at the starting process in a synchronous motor drive. Um, when we were talking about the power angle relationship, incidentally, we also spoke about hunting oscillations. If we have a variable frequency operation in a synchronous motor drive, or if we are going to have a load change, a substantial load change in a synchronous motor drive. In today's class, we are going to look at V and inverted V curves for a synchronous motor drive. This is particularly looked at for a motor drive which is connected to an infinite bus. So when a motor is connected to an infinite bus, what we mean is in India, for example, if it is 50 hertz and let us say 440 volts, if it is a normal three-phase synchronous motor drive, this is essentially going to be set in stone. These values are set in stone. So we call that as infinite bus. The voltages and the frequency, nothing is going to change. It's all set in stone. So when we are connecting a synchronous motor drive to an infinite bus, the applied voltage V, if I may call this as V armature, which is the applied voltage, that will not change. And the synchronous reactance of the synchronous motor drive, which is XS, which is actually 2 pi F L S, where synchronous inductance is Ls. So this will also not change because frequency is a constant. And frequency being a constant, if at all we want to change something, we might have to change the field current or excitation. So field excitation can be adjusted in this particular case. Okay. So what we are looking at in this particular discussion regarding the synchronous motor drive is if the load is a constant, that is load power is a constant, then how does the excitation affect field current, armature current? What I mean is if I vary the field current, how does the armature current change and power factor change? These are the two things that we are going to look at when we are talking about this synchronous motor drive. So let us say here is my voltage that I'm applying from the infinite bus to the synchronous motor drive. And here is the synchronous reactance of the synchronous motor drive. And this is what is actually E angle minus delta, which is the excitation voltage. So this excitation voltage, we already said E is equal to 4.44 F phi multiplied by number of turns. This is valid whether it is a transformer or whether it is synchronous motor drive or induction motor drive. All of them are going to follow this equation. So in one sense, we can say the excitation voltage will be proportional to flux. So, which is also indirectly proportional to the field current. And generally in a synchronous motor, when we are just giving sufficient flux from the field side, that is the rotor side, then if we are delivering a particular torque, electromagnetic torque TE, then it may just draw a current from the power supply, which is IA, which is just sufficient to produce the torque by interacting with the flux. The flux is actually created by the field current. But if we don't give sufficient amount of field current, then what is going to happen is the flux, what is actually created in the air gap, may not be sufficient enough to even produce the torque. So the armature current we draw not only has to produce the real power, which is actually manifesting in the form of torque, but it also has to supply the shortfall in the magnetic flux. So if we are talking about the field current, if IF is just sufficient, then what we actually see as armature current will have only real component. It will not have any reactive component at all because it has to just produce the torque, nothing more than that. So this will be at unity power factor. It doesn't have to really supply any excitation or flux at all. If IF is just sufficient, but if we are going to have IF is slightly less than what is needed by the machine to produce the torque. In that case, what is going to happen is some flux has to be compensated for from the armature side. So, which means it has to supply some amount of reactive power. So from the armature, not only the armature current comes, which is at unity power factor, but some amount of reactive current also comes. So that is the reason why IA will have some reactive or magnetizing component. And the moment you say it is a magnetizing component, it will have definitely an inductive effect. That means it will have lagging power factor. On the other hand, if IF is going to be or is provided in excess. So from the rotor side, what we supply as the magnetizing current or the field current is in excess of what is actually required. Then in that case, what is going to happen is some amount of reactive current will be returned to the three-phase supply from the armature side. So this will actually work like a capacitor. So you will see normally a leading power factor. So there will be a leading power factor visualized from the armature side. Let us try to take a look at this in terms of a phasor diagram. So let us say I am having the excitation voltage somewhat like this. So this is the excitation voltage. Okay. Now we are going to let me probably start with infinite bus voltage, which is going to be our reference. So let me say this is my infinite bus voltage, which is VA, which is actually VA angle 0. We are talking about this as the reference. Initially, I'm going to take an armature current, which is actually something like this. So this is going to be my armature current. Let me call this as IA1 because I'm taking the first case where the armature current is lagging behind the supply voltage by an angle phi 1. So this is the armature current. Now, very clearly, I am going to have IA cos phi 1, which will be along the horizontal axis. So this is going to be IA cos phi 1. So this is the real component of the armature current. So I can write VA times IA cos phi is going to be the power. What is supplied from the synchronous machine per phase. So if I multiply this by 3, then this is going to be the 3-phase power. So if I say that the power is a constant, if VA is a constant because the machine is connected to an infinite bus, IA cos phi should also remain as a constant at constant power. So that's what I mean by writing here IA1 cos phi 1. This has to remain as a constant if we are talking about constant power operation of the synchronous machine. So I am just drawing the trajectory of IA, where IA cos phi 1 is a constant, whether IA is remaining here or wherever, I'm going to have IA cos phi 1 only coming from this point, if I may call this as O until P. So OP happens to be the real component of current in the case of the synchronous motor drive operating at constant power. So let me remove these two. And let me take a look at now if this is IA1, from what we drew as the equivalent circuit, I should be able to say that whatever is my VA minus JXS times IA being the current vector, that should be equal to E angle minus delta. So I have to subtract J excess IA from VA to obtain what is the excitation voltage. Let me try to do that in the phasor diagram. So if I want IA J excess, because it is a reactance voltage or inductance voltage, it has to lead the current by 90 degrees. So I should have something like this as my IA1 JXS. So if I want minus IA1 JXS, it will be exactly opposite to that of this. So I can draw it somewhat like this. This is going to be IA1 JXS with the minus sign. So let me erase this now. Now, if I try to add these two, that is minus IA1 JXS with VA, then I should be getting what is my excitation voltage E. So this is going to be E1. So I'm talking about IA1 as the armature current at a lagging power factor, IA1 times JXS minus of that as the drop that is taking place in the synchronous reactance. And when I sum up VA angle 0 and IA1 JXS minus with the minus sign, I'm getting E1. So this happens to be E1 or excitation voltage. So this is the case when I am talking about a lagging power factor current is being drawn by the synchronous motor. Let us say I want to have the same power. So this is the locus of IA cos phi. We already said this is the locus of IA cos phi. Under this condition, if I look for a unity power factor current. So if I just have a unity power factor current, I should have it somewhat like this. This is the unity power factor current. So this is going to be IA1. So IA1 happens to be the unity power factor current now. So when I have the unity power factor current, if I try to get what is IA1 JXS, it will be like this because it will be perpendicular to the unity power factor current. So let me call this particular current as IA2 rather than IA1 because IA1 happened to be the lagging power factor current. IA2 is the unity power factor current. So I'm going to have this somewhat like this. So let me again erase this and redraw this particular current. So it should be exactly vertical. Previously, what we drew was this is IA2JXS. So this will be minus IA2JXS. Whereas what we drew here was minus IA1JXS. Okay. So we got this as minus IA2JXS. So when I add VA angle 0 to this minus IA2JXS, now the newer value of excitation voltage is here. So this blue colored vector, which is E2, which is longer than E1. So if I look at E1's magnitude, it is smaller than E2's magnitude. So this E2 happens to be longer, and that is actually corresponding to the excitation voltage when I am having a unity power factor current. Rather than that, if I am going to have a leading power factor current. So let me probably take a leading power factor current. So this is IA3. And it so happens that even in this particular case, IA cos phi is still a constant. So this is IA3. If this is IA3, IA3 times JXS will be somewhat like this. This is going to be IA3 times JXS. So when I draw minus IA3 times JXS, it should be somewhat like this. So this will be minus IA3 times JXS. So when I add this to VA angle 0, I'm going to have the excitation voltage somewhat like this. So this is going to be E3. And you can see that E3 is even longer than E2. And we already said that excitation voltage is proportional to flux or field current. So if at a given value of frequency, if I'm going to have more and more magnitude of excitation voltage, I should be able to say the excitation voltage magnitude can increase only if IF1 is smaller than IF2, which is smaller than IF3. So you can very well see that when IF1 was really minimal, at that point it was a lagging power factor or mature current, and I was having an excitation voltage which was also smallest. Now, when I increase the excitation current slightly, it went to unity power factor, and during unity power factor, you can very well see that it is only the adjacent side of this right angle triangle. If I'm talking about this as the right angle triangle, OPQ as the right angle triangle, OP happens to be the adjacent side, only that much is the armature current during unity power factor condition. So this is IA2. Whereas here it was IA1. IA1 magnitude was greater than IA2. Similarly, IA3 magnitude is also greater than IA2. Whereas if I increase the excitation further to IF3, the power factor went to leading condition. It came to 5.3, which is the leading condition. And when you have a leading power factor, under that condition, again the armature current increases. Whereas the power factor has moved away from unity power factor to leading power factor condition. So this essentially tells that in a synchronous machine, we would be able to adjust the power factor by adjusting the field current. If I adjust the field current, I'll be able to adjust the power factor in a wound field synchronous machine at a given power deliverability of the machine. Still, we would be able to adjust the power factor appropriately by adjusting the field current. The same way, the magnitude of the armature current can also be minimized if I am trying to operate the machine at unity power factor condition. This has a major implication in terms of the inverter that we use for controlling a synchronous motor drive. If I try to operate it at unity power factor condition, the current drawn by the synchronous motor drive is going to be minimum. So if let us say here is my source, the infinite bus source is here. And from the source, I'm going to connect through a long cable to the inverter. And from the inverter, it is going to be connected to the synchronous motor drive. Then this long cable again can be of smaller thickness if the current is decreased because of unity power factor condition. And that will also reduce the I square R losses. That is one reason why synchronous motor drives are preferred whenever we talk about a few megawatt level of motor drive. Because in a few megawatt level of motor drive, even if I square R losses are decreased slightly, the efficiency is improved even by 1 or 2%. It's a big deal because it is going to minimize the amount of power loss to a large extent. Because in megawatt level, even 1% efficiency improvement will really impact how much energy is saved, how much power is saved. That is one reason why synchronous motor drives are generally used whenever we talk about few megawatt or few tens of megawatt level motor drives. Whenever we use, we worry about the efficiency quite a bit. And that is the reason why synchronous motors are fast replacing all the induction motors, because induction motor efficiency is normally lower due to it operating always at lagging power factor. Now, I cos phi is a constant when we are talking about power is a constant. Similarly, we also said EV divided by XS sine delta. That is also power. So this is also power. And if we are talking about V is a constant because it is connected to infinite bus. The machine is connected to infinite bus. Xs is also a constant because the machine is again connected to a constant frequency source. Then for a given power, E times sine delta, this will remain as a constant. Just like how we said I cos phi will remain as a constant, E times sine delta will be a constant. So if I just extend this further, and this is what is our E, and between E and V, whatever is the angle, we call that as delta, and this is delta 3. So this is actually E sine delta. So E sine delta will be a constant whether we are talking about condition of lagging power factor condition or leading power factor condition or unity power factor condition. Under unity power factor condition, this blue color, vector, that is what is unity power factor condition, which is corresponding to IAJXS. And this green color vector corresponds to IA3JXS, which is corresponding to the leading power factor condition. And this black color vector, what we saw, that is actually corresponding to IA1JXS, which is actually the lagging power factor condition. In all the three cases, E times sine delta is actually equal to this particular vector itself. So E sine delta happens to be a constant, or I cos phi happens to be a constant when you are talking about constant power condition. Now, we said that the armature current happens to be the lowest under unity power factor condition. So if I try to plot what is the armature current, with respect to the field current under a given power, we are going to see that the armature current will be minimum at a particular field current. And on either side, you are going to see that this particular armature current increases. So if this is the IA minimum value, and this is also corresponding to, let us say, IF dash, which is giving you the minimum amount of armature current for a given load. And this side is IF less than whatever is IF dash. So this will be lagging power factor condition, whereas this is going to be leading power factor condition. And this is for a given load, let us say at P1. If I increase the power to P2, very clearly I'll be requiring more amount of armature current. And that armature current very clearly is not going to occur. The minimum amount of armature current for another load is not going to occur at the same IF dash. So if I try to draw for another load condition, I may have it somewhat like this. So I may have this as IF2 dash, which will actually correspond to another load condition, which is P2. So P2 load condition is greater than P1. And if I say that this is IA1 minimum and this is IA2 minimum. So IA2 minimum is going to be greater than IA1 minimum because the load is also increased. That is the reason. So this is the way you are going to see the V curve. So the V curve is always plotted in such a manner that the armature current versus the field current variation for a constant power. And inverted V curve is somewhat like this. So if I have the field current here and I am looking at the power factor. So the power factor maximum can be 1. And that happens at a particular field current, which is in this particular case, IF dash. So for a power of P1 output, I'm going to see that the power factor actually goes somewhat like this. So this is going to be unity power factor here. So let me again draw this. So this is the power factor, and this happens to be the unity power factor. And this is going to be lower than 1. This side also is going to be lower than 1. And unity power factor occurs at a particular field current, which is IF dash. And this corresponds to a power P1. So we are going to have lagging power factor on this side and leading power factor on this side. And this particular curve is generally known as inverted V curve. So inverted V curve is plotted for power factor versus field current variation for a given load power. If the load power is a constant, under that condition, if I try to look at how exactly the power factor is varying with respect to field current, that is essentially giving you inverted V curve. So one thing I would like to say as the greatest advantage of wound field synchronous machine is that it will allow you to adjust the power factor as per your requirement, whether it can be in leading condition or lagging condition or at unity power factor condition. That can be done only by adjusting the excitation. And when you adjust the excitation, you would be able to minimize the current drawn by the synchronous motor at a particular load condition, which automatically reduces the inverter rating It will also reduce the I2R losses in the in-between cable from the source to the inverter to the motor drive. So all these things contribute in a big way towards improving the efficiency of the synchronous motor itself. Now we said that the power is EV divided by, let me write it again. The power is given by the equation EV divided by XS sine delta. This is multiplied by 3. Now, the delta at the most in steady state can be 90 degrees. It cannot be more than that. So when you try to increase the load slowly in a synchronous motor, you can go at the most 3 times EV divided by XS. This is the maximum power that can be delivered by the synchronous machine. And the maximum torque, if I try to write corresponding to this maximum power, it will be 3 EV divided by XS omega S, where omega S is mechanical synchronous speed of this machine. So this is going to be the maximum torque. Sometimes this is also called as pull-out torque. This particular torque is generally known as pull-out torque because if you try to load the machine beyond this torque value, then the machine will pull out of synchronism. It will not be able to run as a synchronous motor anymore. This is the maximum torque that can be developed by the machine, not anything more than this. And that's one reason why it is called pull-out torque. So let us try to work out one problem in a synchronous machine, a numerical example that I'm going to work out. So let us say numerical example for a synchronous motor drive. So the problem statement is somewhat like this. A three-phase 6.6 kilovolt, 6-pole, 1.1 megawatt, 60 hertz, UPF, unity power factor, Y connected synchronous motor has a synchronous reactance of 36 ohms. Field resistance is 5 ohms. And armature resistance is 0 ohm. It is negligible. Rated field current is 12 ampere. Calculate the load angle delta at full load condition with rated IF. Second thing that is being asked is pull-out torque. The third one that is being asked is power factor. Calculate power factor and armature current at half the rated torque and at rated IF. Fourth one is field current to obtain unity power factor at half rated torque. So these are the 4 subdivisions that are being asked. Now let us try to work out the solution for this. So first of all, I think it is very important to calculate what is the rated armature current. What this problem says is the machine is going to be at unity power factor condition. That means whenever we are talking about rated IF and full load condition, the machine is going to be at unity power factor condition. That's what it implies. If it says unity power factor Y connected synchronous motor, unity power factor is actually the condition under which full load is being supplied at rated frequency at rated field current. So 1.1 megawatt, so 1.1 multiplied by 10 power 6 is going to be equal to 3 VIA cos phi. 3 VIA cos phi. And cos phi is already given to be unity. This is given to be unity. So we can directly write this as, if we are talking about per phase voltage, it is 3. Otherwise, we should say root 3 VL IL cos phi. That is also fine. Line current and line voltage. And here we have been given it is star connected machine with 6.6 kilovolts of voltage. So we can write this as root 3 times 6.6 multiplied by 10 power 3 multiplied by IA. So from which we can calculate IA as 1.1 multiplied by 10 power 6 divided by root 3 divided by 6.6 divided by 1000. So IA comes out to be 1.1 multiplied by 10 power 6 divided by root 3 multiplied by 6.6 multiplied by 10 power 3. And this comes out to be 96.225 ampere. So this is the rated IS value or armature current value. Now, what is being asked is calculate delta at full load condition with rated IF. So we have got already what is the value of armature current. So we can say E angle minus delta equal to V minus J excess IA angle phi. Here, this phi, power factor angle happens to be because it is unity power factor, phi is 0 degree. So there is nothing to write there. Now we can write E angle minus delta is equal to 6,600 divided by root 3 because it is per phase voltage minus J. Excess is 36 ohms. So I can write J times 36 multiplied by 96.225. Okay, so we can do the complex number calculation. This happens to be 3810.5 minus this 36 times 96.225 multiplied by J. So I can write this as J 36 times 96.225. So this comes out to be 5149.75 angle minus 42.3 degrees. So this is the excitation voltage we have calculated. Now, in this, whatever is here, that happens to be delta, and this is the magnitude of E. And this delta watt is given here is electrical value. So delta electrical is minus 42.3 degrees If I want delta mechanical, please note this happens to be a 6-pole machine. So you can say 1200 RPM is the synchronous speed. And if I want to write it in radians per second, this has to be multiplied by 2 pi by 60. So that comes out to be 125.66 radians per second. So in this particular case, electrical to mechanical conversion, it has to be divided by 3. So almost approximately 14 degrees happens to be approximately delta. That is the mechanical value. Delta mechanical is 14 degrees. So the first subdivision where delta has been asked, that has been solved. The second one is pull out torque. So pull out torque, just now we just discussed. So pull out torque is equal to EV divided by XS multiplied by 3. This will be pull out power. This has to be divided by omega S. So in this particular case, E happens to be 5149.75. And V happens to be this. So that is 3810.5. This divided by XS is 36, right? Because synchronous reactance is given to be 36. And the synchronous speed is 125.66. So I have to multiply this by 125.66 radians per second. So this is the pull-out torque. And pull-out torque comes out to be 13.013 kilonewton meter. So this is the pull-out torque. Now the third subdivision, what is being asked in this particular case. So the third subdivision is power factor and armature current at half the rated torque and rated IF. So IF remains the same. Torque nu is half the rated torque. That's what is given. So first thing we have to remember is we said E is proportional to IF. So if IF remains the same, E will remain the same. It cannot change. Okay. Now, if E remains the same and torque is half the rated torque, 1.1 multiplied by 10 power 6 divided by 125.66. That is power divided by omega S. This is what is the torque. So this is the rated torque. So half the rated torque, that will be essentially 1.1 multiplied by 10 power 6 divided by 2 times 125.66. And this comes out to be, half the rated torque comes out to be 4376.9 Newton meter. This is half the rated torque. Now, what is given is power factor and armature current has to be calculated at half the rated torque and rated IF. That is what is being written. So, because E will not change, we should be able to write this as 3 times V dash divided by excess omega s sine delta dash will be equal to 3 times E already we calculated, which is 5149.75. And V also we calculated, which is 3810.5. So 3 times 5149.75 multiplied by 3810.5 divided by 36, and omega s is 125.66 sine delta dash. This is going to be equal to half the rated torque, which is 4376.9 Newton meter, from which we should be able to calculate what is delta dash. So delta dash comes out to be 19.65 degrees. So this is electrical. If we want delta to be mechanical, then we have to just divide it by 3. That's not a problem. So delta dash mechanical comes out to be 6.55 degrees. Now what is being asked is power factor and IF at half the rated torque. Now we can use the same equation what we used for calculating the original value of excitation EMF. So we can again use that, saying that E angle minus delta equal to V angle 0 minus J excess IA, angle phi. So I should be able to write this as E, which is actually 5149.75 angle delta is minus 19.65 degrees equal to V angle 0, which is 3810.5 minus J times XS, which is 36, multiplied by IA, we don't know what it is, and phi also, we don't know what it is. These two have to be calculated. So we can actually segregate the above equation into real and imaginary parts. So we have to segregate them into real and imaginary part. And this actually gives us the value. IS is 56.09 ampere, and cos phi happens to be IS cos phi is 48.10. So we can say this is 48.10 divided by 56.09, and it is 0.86. The power factor happens to be 0.86 in this particular case. Okay. Now, if we are looking at the fourth subdivision, I think we have finished calculating the power factor. We have finished calculating what is the current. Both are done in subdivision 3. So in subdivision 4, what is being asked is field current to obtain UPF at half the rated torque. So what should be the field current rather than having this kind of power factor? If I want to have unity power factor to modify the power factor to unity in half the rated torque. What should be IF? What should be IF? That is what is being asked. So if I want unity power factor condition, so under unity power factor condition, I should say 514, sorry, 5149.75 angle minus delta. That should be equal to 3810. Wait a minute. If we are modifying IF, then even E will not be a constant. So we cannot write E as a constant. So the torque is half the rated torque. That is already given and it is unity power factor condition. So we should be able to write this as the torque is half the rated torque, which was 43 something, 4376.9. So we can say 4376.9 Newton meter is equal to 3 V IA cos phi. So that is going to be equal to 3 multiplied by 3810.5 multiplied by IA, and cos phi is unity because we want it to be at unity power factor condition. So in which case IA can be recalculated, and IA comes out to be, in this particular case, 48.113 ampere. If I may call this as IA2 dash, corresponding to half the rated torque and unity power factor condition, this is what is the armature current. So with this armature current, we can calculate now, this is unity power factor current, so we should be able to calculate E2 dash angle minus delta 2 dash should be equal to, V minus J IA2 dash X. So V is 3810.5 minus J times IA2 dash is 48.113, and this has to be multiplied by XS, which is 36 volts. So this will give us what is E angle minus delta, and that comes out to be, E comes out to be 4185.686 volts with an angle of minus 24.5 degrees. Now, this is the excitation voltage. And excitation voltage is always proportional to the field current. So if we say that in this particular case, 5149.75, this excitation voltage was proportional to 12 ampere. So we can say 5149.75 5149.75 volts. When E equal to this, then IF was 12 ampere. Now, when E dash equal to 4185.686 volts, then the new value of IF2 dash can be calculated based on ratio and proportions. So that should be 4185.686 divided by 5149.75 multiplied by 12. So this comes out to be 9.75 ampere. Please note that originally the field current was 12 ampere. According to the problem, it said that rated field current is 12 ampere. At 12 ampere, when you are having unity power factor and with rated field current, you are able to generate a torque of full load torque, which is almost 8,000 and odd as the Newton meter, and full power of 1.1 megawatt. Whereas when you reduce it to half the rated torque, if you keep the field current at the same situation, under that condition, we are getting a power factor of 0.86. In all probability, this must be a leading power factor because you have excess amount of excitation. That is 12 ampere of field current is being fed. And you are deriving only or drawing only half the rated torque. Whereas in the last subdivision, we wanted to make the power factor as unity. The power factor has been made unity. Because the power factor has been made unity, for that, the field current has been decreased from 12 ampere to 9.75 ampere at half the rated torque condition. And still the machine is able to deliver half the rated torque at unity power factor. So as the load on the machine decreases, even lower excitation will be able to do the job. Lower value of field current will be able to do the job. That is the bottom line. So in the next class, we will be looking at salient pole synchronous machine, and we will also talk about certain aspects pertaining to the starting operation of the synchronous motor. And finally, we will also look at the special cases of reluctance machine as well as the permanent magnet machine. Only after completing all these things, we will go over to braking and speed control of synchronous motor